Yeah,
Oh,
so let's get started. So, hi everyone, thank you for coming. So, this is the first Theory of Computing for Fairness seminar of the semester. Today, our speaker is Seyed Esmaeili, who's right now a postdoc at the Data Science Institute at University of Chicago, where he's working with Haifeng. Before that, he was a postdoc at Simon's Welfare at Berkeley, and he was a PhD student at the University of Maryland. He's done some work at the intersections of algorithms, data, society, fairness, and today he's going to be telling us about his work on doubly constrained fair clustering. So yeah, all yours.
thank you. All right, so I'll talk about doubly constrained fair clustering, which was published in Europe's of 2023. And this project was done with John Dickerson, Jamie Morgenstern, and Claire Zhang. Okay, so let's start with a review of clustering. So clustering is a fundamental problem. It's a fundamental problem in operations research, where it's mostly called the facility location problem. Basically, we have a collection of individuals, and we want to choose a set of points as facilities in such a way that we minimize the distance between the facilities and the individuals. So as you can see in this example, the points might represent individuals, and we'll do clustering with k equal to 2, and we'll end up with an output like this. Clustering is also a fundamental problem in machine learning. In the machine learning setting, we're given a data set of points, and we want to apply clustering in such a way that the output reveals the structure within the data set. So we might be given these collection of points, and we'll apply clustering with k equal to 4, and we'll get these clusters. And basically, ideally, we want clusters that consists of similar points, and different clusters should be dissimilar. Now let's give a more formal definition of clustering. So in this paper, we will in particular focus on the k-center clustering. How do you formally define k-center clustering? Well, we start with the input, which is a set of points C. Every pair of points within the dataset has a distance function, d of I and j, which is supposed to be a metric. And we're given also the number of clusters k. And the output should consist of a set of centers in such a way that the cardinality, the number of points within the chosen set of centers, should not exceed k. Another thing to point out is that the set of centers are subsets of the input data set. And this is a restriction in the k-center clustering. You might not, for example, see it in k-means, where you can choose any point in the space as a center. In addition, we're supposed to give an assignment function, where the assignment function assigns points to centers, okay? Now, how do we find the set of centers and the assignment function? These are obtained by minimizing the clustering objective. So concretely, in the case of the k-center, this is our clustering objective. So in words, this is the k-center clustering basically minimizes the maximum distance between a point and its assigned center. So this is just the maximum distance between a point J and its assigned center. And we're minimizing over the two arguments S and phi, where again S and phi are the chosen centers, and the assignment function, which assigns points to centers. So one thing to note is that the k-center is an NP-hard problem, and therefore we don't think we can solve it exactly in polynomial time. And we're basically in the setting where we're looking for approximation algorithms. Specifically, we're looking for algorithms in such a way that the output is at most alpha times opt, where opt is the cost of the optimal solution. And obviously, we would end up with alpha being strictly greater than 1. And smaller values of alpha are better because that's a better approximation. All right, so we spoke about the assignment function, which assigns points to centers. So maybe you would say, why do we need the assignment function phi? Why don't we just assign each point to its closest center? And this is actually correct in the absence of constraints. So when we don't have constraints, the assignment function is trivial and simply amounts to assigning points to their closest center. So if we're given these set of points, and we're clustering with k equal to 2. And the output can look like this, where we have marked the centers with an X. So there's a center here, the center there. And as you can tell, every point is assigned to its closest center. That's how we get this cluster and that cluster. Now, once constraints are imposed on the clustering problem, the assignment function becomes non-trivial. So going back to the same example, let's say we impose a constraint on the clustering. So we say cluster subject to the constraint that at least 3 points in each cluster, subject to constraint that we have at least 3 points in each cluster. So clearly, this cluster is not valid because it only consists of 2 points, right? And therefore, the output might actually look like this, where we basically added a third point to this cluster to satisfy the constraint of having at least 3 points per cluster. And as you can tell, this point was actually assigned to a center that is further away from it, unlike in the previous case, okay? And I just want to emphasize this because many of the fair clustering problems that have been introduced are examples of constrained fair clustering, are examples of constrained clustering. And therefore, the assignment function in fair clustering is mostly non-trivial, okay? All right, so let's motivate fair clustering. So that's generally not difficult to do. So clustering is a widespread problem. And the motivation for fairness here is similar to the motivation of algorithmic fairness in general. Clustering algorithms could violate fairness of notions. They may lead to inequitable outcomes. And if, in addition, if we impose fairness constraints, we might end up with more desirable outcomes with higher welfare. Okay. All right, so let's give concrete examples of fair clustering notions that have been introduced. So let's start with this example where we have a set of points and the color of the point denotes its group membership. So we basically have 2 demographic groups. One is red and one is blue, okay? And this is an abstraction. So the demographic groups can be anything of race, gender, and so on, okay? So we have an input set of points. One of them is red and the other is from the blue group, and we're clustering with k equal to k equal to 2. So an ordinary clustering would give us this output, where, as you can see, cluster C1 consists entirely of the blue group, whereas cluster C2 consists entirely of the red group. And this might be seen as bad because you have no mixing in the colors in each cluster. You basically have no diversity. So if we were to take this clustering and then apply a post-processing to it, so for example, maybe we will send cluster C1 an advertisement for a high-paying job, then clearly this advertisement would not be seen by any of the red points, right? Because the points here are entirely blue. And this basically motivated the notion of fair clustering, which we'll call group fair clustering and abbreviate by GF. This notion was introduced by Kiraketti et al. In 2017. And it basically says, solve the clustering problem subject to the constraint that there is diversity within the clusters. So concretely, this is just the ordinary case center objective, okay? And a constraint could be that each cluster consists of 50% red and 50% blue, all right? So if we basically go back to the same clustering input, and now we solve it with this additional constraint, the output would look different. It would look like this. So where we basically have diversity in cluster C1 and C2, okay? All right. Let's also talk about another example of fair clustering notion. So again, this is an input set of points, different colors denote different demographic groups, and we're now clustering with k equal to 2. The output could look as follows, where we basically have 2 clusters and the selected centers are marked with an X. And as you can tell, actually, both selected centers are blue. And this might be a problem. So all centers are blue. There is no diversity in the selected centers. In many machine learning settings, you would basically have a data set, you would cluster it, and then you would look at the center associated with each cluster, and the center is called like the prototypical example of the cluster and is seen as a representative of it. And basically in this data set, the output suggests that all of the centers are blue. And this basically motivated a notion of fairness, which we'll call diversity in center selection, and we'll abbreviate by DS, which basically says solve the same clustering problem subject to the selected centers having equitable group memberships, basically. So concretely in this example, it would just minimize the same case center objective, but it would have the additional constraint of one selected center being blue and another selected center being red. So the output following the DS fairness notion would look like this, where we basically have one blue center and one red center. All right, now we will talk about another fairness notion, and this fairness notion, unlike the previous two, is an individual fairness notion. Okay, and we'll keep in mind an operations research setting where the centers represent facilities that are providing a service. Okay, so let's say that we have these collection of points and that we are clustering with k equal to 2. Then the output can look like this. And as you can tell, the first cluster C1, the center there, which is a facility that's providing a service, it has a high service load in comparison to the other cluster, which only has 2 points. So in general, we see that dense regions tend to have a higher service load. And another observation is mostly in operations research, when you see a low density region, that tends to correspond to a rural area. And residents in rural areas can travel larger distances because they have better means of transportation. Therefore, we can assign them larger distances to the facility. Okay? And these observations basically motivated the neighborhood radius fairness notion that was introduced by Young et al. In 2019. So what does this fairness notion say? Well, first, it associates with every point j in the data set the neighborhood radius nr of j. What is nr of j? Basically, you place a ball whose center is at point j, and you keep expanding it until it encloses at least 1 over k of the population. Okay? So, until it encloses 1 over k of the population. So, in the above example, we had k equal to 2. The population number of points is 18. So 1 over k of the population is 9. What the neighborhood radius fairness notion says, it says solve the ordinary clustering objective subject to the constraint that the distance between a point and its assigned center is at most the neighborhood radius. So this allows for again, going back to low density regions, if the region has low density, then naturally we would expect the neighborhood radius to be larger, right? So if we apply this fairness notion to this example, we would end up with a different output that looks like this. And as you can tell, the service load is more evenly distributed, and these 2 points have a larger distance to the center, but we think that's okay because again, they're low density regions, so they represent rural areas where the individuals have a better means of transportation. Okay? All right. So just some notes about fairness notions. Like all other fairness notions, we generally have group versus individual fairness notions. The GF and DS notions we talked about, which basically say there should be diversity in the cluster, and the other one that says there should be diversity in the selected centers, they're both examples of group fairness notions, which basically take group memberships as inputs. And the last notion we talked about, the neighborhood radius fairness notion, is an individual, not group fairness notion. And if you basically remember, it does not take the group memberships as an input. Another thing in clustering, we can also divide the fairness notion as either being representation-based or distance-based. So the neighborhood radius fairness notion actually takes distance as input, okay? Basically, distance is needed to decide whether a given solution is feasible or not, whether it satisfies neighborhood radius fairness or not. But that was not the case in the GF and DS notions. They do not take distance as input, and they need the group memberships instead, right? Okay, so let's give our view of the current state of fair clustering. So we've seen significant interest in fair clustering since the paper by Kiraketti et al. In 2017. So a general sketch of a paper can be seen as follows. A general sketch of a large collection of papers is that they basically identify something bad, and then they solve the clustering problem subject to that bad thing not happening. So as an example, the bad thing could be that the colors don't mix in the cluster. The cluster has no diversity. And the paper suggests that we should solve clustering subject to the constraint that the colors mix in the clusters, okay? And we basically see this. So you see one paper identifies a bad thing B1, and then it proposes that the clustering objective be minimized subject to a constraint C1, which forbids B1. Then we find another paper which identifies another bad thing B2, and then proposes that we solve clustering subject to C2, which forbids B2, and another B3 subject to also C3. And right now we have at least 7 different fairness notions that have been introduced in clustering. And each one of them is actually motivated disjointly. So as you remember, as I went through the different fairness notions, GF, DS, and neighborhood radius, there isn't really a discussion of how these notions relate to one another or how they build on basically previous work. So based on this, it seems that some questions are reasonable. So the first one is, how do the constraints relate to one another? The second question is, if each one of them is well motivated and there's a good reason to satisfy the constraint, then why should we satisfy one? Why should we not satisfy all of them simultaneously? That is the intersection of the constraints. And the third question is, are there constraints which are incompatible with one another? So as we remember the paper by Kleinberg, Mullainathan, and Raghavan in fair classification, we have a result that shows that calibration and balance cannot be satisfied simultaneously, despite both of them being desirable. So could something like this be happening in clustering as well, where we are unable to satisfy different constraints simultaneously? And this is basically the aim of our project, Doubly Constrained Fair Clustering. So we're basically taking a first step towards understanding how the different fairness notions in clustering relate to one another. So since we have to start somewhere, we pick the concrete question of how to satisfy both the GF and DS notions simultaneously, or what we call GF plus DS. So again, GF and DS, GF it says diversity within the cluster, and DS says diversity in the selected centers. And we ask questions like, if you basically satisfy one constraint, either GF or DS, can you get the other for free? Or for example, how do GF and DS relate to other fairness notions that have been introduced in clustering? All right, so let's just make the problem clear with an example. So we have this input instance where we have red and blue points. Now, ordinary clustering can give us an output like this. And as you can tell, each cluster consists mostly of one group. So C1 is mostly blue, C2 is mostly red, and both selected centers are blue. So this is an output that neither satisfies GF nor DS. Now let's look at this output. And this output, we basically have GF satisfied because each cluster consists of 50% red, 50% blue. Again, this cluster is also 50% red, 50% blue, but both selected centers are blue, so they do not satisfy DS. Now, in this example, we have a clustering output where we have one blue center, one red center, so we satisfy DS, but again, each cluster basically has little diversity, overwhelmingly consisting of one group. Here, almost entirely red, and here almost entirely blue. And this is basically the output that we're looking for, which satisfies GF and DS simultaneously. As you can tell, every cluster has a 50-50% representation of both groups, and one center is blue and the other one is red. So we have diversity in the selected centers. Now let's just give a formal definition of our problem. So our objective is the K-center objective, and we have two sets of constraints. The first is the GF constraints. So just to clarify the notation, Ci is the set of points in cluster I, and this is the cardinality. So this is the number of points in cluster Ci, and this, the cardinality of Ci blue is the number of blue points in cluster I. Similarly, this is the number of red points in cluster I. And the GF constraint is basically one's proportional representation in each cluster. So this is telling us that the number of blue points should be upper and lower bounded by some fraction times the entire set of points. So for example, if the data set was 50% red and 50% blue, we might expect the upper bounds, U blue and U red, and the lower bounds, L blue and L red, to be set to values like 60% for the U's and 40% for the L's, okay? This is basically saying at least 40% blue and more 60% blue in each cluster, and similarly for the red set. The DS set of constraints, which basically wants diversity in center selection, would say something like as follows. So it says the number of points, the number of red centers should be lower bounded by some pre-specified number, K lower red, and upper bounded by some pre-specified number. And the same thing for the blue centers that were selected. Okay. All right. So a good question is, why among the 7 different constraints are we choosing GF and DS? We don't have an answer here in the form of a theorem, but we basically have the following motivations. Well, both of them are group fairness notions, not individual fairness notions. Both of them are representation-based, not distance-based. And when we say representation, we mean to decide if the point is feasible or not. We just need to look at the group memberships, not the distances. And so therefore, it seems like the right place to start if you have, you know, a large number of constraints, more than 7. All right. Now we'll make a remark on a property that the selected centers have to satisfy. So let's consider this example where we have 4 points, 2 of them blue and 2 are red, and the distance between the points is simply the path length distance. So one thing to note is the statement of the problem says that the set of centers, the cardinality, the number of chosen centers should be less than or equal to K. It actually doesn't say that the number of centers should equal K. Now this is in general not relevant in clustering settings where you don't have constraints. But and the reason is simple. So if you have a clustering solution where K is equal to 4, but the set of centers chosen is 3, you can just choose an additional point as a center and assign it to itself. So you can, given a solution where the number of centers is strictly less than K, you can easily convert it to a solution where the set of centers is equal to K. But this becomes relevant in constrained clustering. This being that the number of centers is less than or equal to K. And if we don't allow this, then we can have instances that become unfeasible, whereas they would become feasible if we just allow the set of centers to be less than or equal to K. Now, this simple note can actually cause us some trouble when we want to satisfy the GF and DS constraints simultaneously. So again, going back to this example where we have 4 points, let's say that we select 2 as a center and 4 as a center. We clearly satisfied DS because the centers chosen are diverse. One of them is blue, the other one is red. let's consider two solutions. We in addition have to satisfy the GF constraint, that is the clusters should have diversity. Let's say in the first solution, we assign all of the points to point 2. Then we'll end up with two clusters. The first one is basically the entire data set, 1, 2, 3, 4, and the other one is completely empty. This solution actually satisfies the GF constraint. The first cluster is clearly diverse in terms of the representation of the groups, but the second one is basically empty, and that's actually a special case of being diverse where the cluster is basically has 0 points. Okay, now let's consider another solution where we assign points 2 and 3 to center 2, and we assign points 1 and 4 to center 4. So we'll end up with the following clusters, 2 and 3, 1 and 4, and it's clear that each one of them is also diverse. Now, which solution should we pick? We argue that we should always pick the second solution. And the reason is that the first solution, although it's diverse in the selected centers and diverse within the cluster, basically center 4 in that solution has no points assigned to it. And therefore, it's basically like it doesn't exist, right? So it's functionally non-existent. And that's why we basically impose the following bound, that the selected centers should be active. And what we mean by active is that they should always have non-empty clusters. So basically, solution 1 here is not good because it has, although the centers are diverse, the second center is basically has no cluster assigned to it. Okay. Now we note that basically now we want every cluster to have a non-empty cluster associated with it. This is actually not trivial to satisfy in GF, and if you basically want both constraints, GF and DS. So ordinarily, if a center is not active, then you can just assign it all of the points within a small radius.
Wait, sorry, can I ask a quick clarifying question? Because I think I missed something. How come 4 wasn't assigned to itself in that last example? Like in the first solution, if you
Right.
still have 4 as a center, why is at least
Right, so you can actually assign centers not to themselves.
okay?
It's valid, actually. I agree that it sounds weird, but you can actually have clustering solutions where the center is not assigned to itself. And
Okay.
all right.
And then when you drop, like when you prevent having these empty centers, do you not just end up having like the same problem, but like, you know, like one level up where like now you end up with like 1, 2, 3 assigned to center 2, but then 4 assigned to itself?
You know, what is the problem that I could end up with? Could you...
Like, it seems like maybe if your algorithm was naturally assigning 1, 2, 3, 4 to center 2 and nothing to center 4, then if I add the constraint that you aren't allowed to admit solutions that include a center that doesn't have anything assigned to it, then the algorithm would simply assign the center to itself and not do anything else? Or am I misunderstanding something?
Right. So, okay. So our point is that it's bad when the cluster is empty. Okay.
Yes.
And what we want is to make the cluster not empty, but we want to make it not empty in such a way that it also has diversity in the
Right. Okay. So it wouldn't, if it assigned 4, then it wouldn't satisfy the diversity constraint. So it would also be required to include 1.
Yes, yeah, exactly. Yeah.
Great. All right. Thank you for the clarification.
Yes. And this is actually our point as well, like you were saying. So basically, to make center active, we have to assign at some points, but this is actually is even more difficult in our setting because we can't, for example, just assign it to itself. We have to make sure that it receives a total number of points in such a way that there's diversity, right? So we can't just point 4 here was red, so we can't just assign 4 to itself because that's not diverse. We have to, in addition, send it 1 so we get diversity. All right.
Thank you.
Right. So, okay. So how do we solve, right? How do we solve GF plus DS? So we follow a modular approach. So right now we already have algorithms that satisfy GF, and we have algorithms for DS. So our approach is basically based on using an algorithm for one of them. That is, given a GF solution, can we post-process it to satisfy GF plus DS? Or, for example, given a DS solution, can we post-process it to satisfy GF plus DS? Okay. So our fundamental subroutine, which we use in our algorithms, is what we call the divide subroutine. So at a high level, the subroutine takes a collection of points, which are basically supposed to represent a cluster. And these set of points already satisfy the GF constraint. That is, the colors within the set are well mixed. And what we want is to divide the cluster into subclusters in such a way that each subcluster, in addition, satisfies the GF constraint. And basically, we also change the color assignments of the center in such a way that we have diversity in the selected centers. So at a rough level, basically, the subroutine takes a cluster which satisfies GF and makes it, in addition, satisfy the DS constraint. So if we take the following as an example, so this is a set of points. They clearly are. We clearly have diversity within the group memberships. The center is I, which is blue, and we basically want to, instead of having a blue center, we want to have one green center and one red center. So if we apply the divide subroutine to this set, we'll get an output that looks like this, where one center is now green as we want, and the other center is red. And as you can tell, within each subcluster, we still have the colors mixing well. All right, so now let's give a more formal statement about the divide subroutine. So given a collection of points C with center I and radius R, where basically the radius is the maximum distance between a point and center I, if the set of points satisfies GF and we're given a subset of points Q, so Q is a subset of C, then divides does the following. It will basically turn every point in the set Q into a center. So every center Q within Q is basically going to become an active center. That's one thing. Every center Q will have a subcluster that satisfies the GF constraint at an increased additive violation of at most 2. Now, what do we mean by an additive violation of at most 2? We can clarify this with this example. So let's say that we have a constraint that says CI blue is at most U blue CI. This is a completely fair solution which has no violation at all. If we allow an additive violation of 2, then CI blue is at most U blue CI plus 2. And I want to emphasize that the plus 2 is not in the percentage, but in the total number of points. So concretely, if U blue is 0.5 and CI has 100 points, then basically 0.5 times 100 is 50. If we allow an additive violation of 2, then it's at most 52. Okay, and that's basically what we mean by the subclusters having an additive violation at most 2. And the third thing is that every center Q now has a subcluster, right? The radius of that subcluster is at most 2R, so twice the radius we started with. All right, and a note we make about the divide subroutine is that it runs in linear time, which is basically very fast. It's a linear sweep over the set of points. All right, so let's give a sketch of our algorithm that takes us from a solution that satisfies GF to a solution that satisfies GF plus DS. So again, we're given a solution that satisfies GF at radius R. The solution basically consists of clusters, which we might think of as buckets that satisfy GF. So for example, the solution can look like this: C1, C2, and C3. As you can tell, each one of them has a diversity in the within the cluster. Now, we have in addition the DS constraint now, which could say, I want one red center, I want one blue center, and 2 green centers. So the algorithm works by doing the following. in the first step, it essentially marks the points of the right color assignments. So we basically want one red, one blue, and two green. That's what it's going to do. It marks one red, marks one blue, and marks two green. And afterwards, basically calls the divide subroutine within each cluster to basically divide it. So clusters C1 and C2 are not divided because they basically just have one center, and we just choose one center per cluster, so they're not split into subclusters. But cluster C3 here, which has two centers, actually ends up getting split into two. But again, the divide subroutine gives us bounds on the increase in the radius. All right, so we end up with this theorem, which basically says, given a GF solution of radius R, we can get a solution that satisfies GF plus DS at a radius of 2R and an additive GF violation of 2. And one thing to note is that the runtime of the algorithm is actually, again, linear in the number of points. Now, it follows as a corollary that whenever you have a GF solution, you can, in addition, satisfy DS at an increase of 2R. It follows as a corollary that if we have an approximation algorithm of approximation ratio alpha GF for GF, then we can get an algorithm for GF plus DS whose approximation ratio is 2 alpha GF at an additive violation of 2 for the GF constraint. All right, now, how do we go from a solution that satisfies DS to a solution that satisfies GF plus DS? Okay, so we're given a solution that satisfies DS, basically has diversity within the selected centers, but the colors do not mix well within the clusters. The set of centers is already fixed and decided in the DS solution. So in addition to satisfy GF, what we do is that we set up a linear program in such a way that the points are routed to the selected centers such that the colors mix within each cluster. Now we note that if you were to set up the integer program for this problem, then it actually turns out to be NP hard. So, and that's why we use a linear program. Now, if you use the linear program, then the output will be fractional in general, and therefore you need to follow it by a rounding step. And we use a max flow-based rounding method to get the final integral solution. So now that we basically have routed points to the centers in such a way that they mix, we note that in addition that some centers might actually end up being closed. That is basically, they become non-active, as we pointed out. And since we want active centers, then we actually, our algorithm follows another step where it basically picks additional points as centers and calls the divide subroutine. So this is the sketch of the algorithm, and this is the guarantee that we end up with. So given an algorithm of approximation ratio alpha DS for DS, we can get an algorithm for GF plus DS of approximation ratio 2 times 1 plus alpha DS, and an additive violation for GF that is at most 3. All right, now let's talk about the price of fairness. So the price of fairness, as we know, is the cost of the fair solution over the cost of the agnostic or unfair solution. And basically, because the unfair solution has no constraints, and the fair solution basically imposes a constraint, the POF is in general greater than or equal to 1. So we have a theorem that basically says that for any values of k greater than or equal to 2, GF in general has an unbounded price of fairness. And to see this, consider the case where k equals 2. So an ordinary clustering would actually have a radius of 0, because we would just have the red set here as a cluster, we would have the blue set here as a cluster. But this is clearly not satisfying GF because the colors don't mix within the cluster. So we basically, and the only way to make the colors mix is for us to route blue points to the red points, to the blue points, or route blue points to the red points. And that means an increase in the clustering cost of value R. So basically, that means that the price of fairness is in general unbounded for GF. Similarly, for DS, we can show a similar result, that the price of fairness is unbounded. So consider this example where the green and red points here are actually coinciding. So if we set k equal to 3 and just apply ordinary clustering, then we'd end up with a cluster here, cluster there, and a cluster there, all of them at a distance of 0 from the center. But if we basically impose a DS constraint that says we need one green center, one red center, and one blue center, then obviously, because we have two centers here, and we have two different set of points separated by a distance r, but we only have one center, one blue center to allocate, we'll end up with a clustering cost of value at least r, and therefore the price of fairness for the DS constraint is unbounded. Now, what if we have a solution that satisfies the DS constraint, that is, the centers are diverse, and we, in addition, impose the GF constraint? What happens to the price of fairness now? So let's start with this input instance. A solution which has diversity in the selected centers can basically be like the optimal solution. One red center here, one blue center there, and the clustering cost of 0. But if we, in addition, impose the GF constraint, then clearly the solution is not valid because the cluster does not mix the different points. And the only way to mix them is, again, to route points from red to blue or blue to red. And therefore, if we start with a DS clustering solution and we impose GF on it, we find that the price of fairness is actually unbounded. Now, let's consider the other question. What if we have a GF solution, a solution that satisfies the GF constraint, and now we impose DS on it? Then we actually show that the price of fairness is bounded and it's at most equal to 2. And the way we show that is actually by construction. So the algorithm which we talked about for converting GF to GF plus DS solutions has an increase in the radius of value at most 2. And therefore, basically, unlike the previous case, if we impose DS on a GF solution, the price of fairness is unbounded. The price of fairness, is bounded by at most 2. And this is basically a more complete picture of our results. So we start with an ordinary or unfair clustering solution. If we basically impose the GF constraint on it, then we find that the price of fairness is unbounded, even if we actually allow for large violations in the GF constraint on the order of n over k. It remains unbounded. Okay, now let's say we start with an ordinary clustering solution and we impose the DS constraint on it. We similarly find that the price of fairness is unbounded. And as we said, if we start from a DS solution and when we impose GF on it, we similarly also find that the price of fairness is unbounded, even again if we allow for large violations in the DS and the GF constraint on the order of n over k. But perhaps surprisingly, again, is that if we start from a solution which satisfies GF, if we, in addition, want to satisfy the DS constraint, then we actually find the price of fairness is bounded and at a netted violation of at most 2 for GF. So this is interesting to point out, because another thing to point out is that the runtime to go from GF to GF plus DS is through an algorithm whose runtime is linear, ON. So this is an interesting result because in some sense it says if you have a GF solution, then you can in addition satisfy DS and your objective function is not going to be degraded significantly. And basically the computational cost is at most linear. So it's not expensive in terms of the objective function. It is not expensive computationally as well, since the runtime is linear. All right. We also discuss the incompatibility with other fairness constraints. So what do we mean by incompatibility? So two constraints are incompatible with one another if they have an empty feasible set in the worst case. Okay, So using proofs similar to the price of fairness proofs, we actually show that GF and DS are incompatible with a set of distance-based fairness notions. And distance-based, again, means a notion that takes distance as input, like the fairness and neighborhood radius we talked about. And this is basically our final view in terms of compatibility. So if we have a DS, this is the DS constraint, this is the GF constraint, they're basically compatible. And this is again by construction because we showed algorithms that satisfy both of them simultaneously. On the other hand, if we consider these sets of these fairness notions, so fairness in your neighborhood, which we talked about earlier, and two more, socially fair and proportionally fair, I've put the references for them because clarifying the notions would actually take significant time. We find that they're incompatible with GF and they're incompatible with DS as well. And this is basically the summary of our results. So if we start with an alpha GF approximation for GF, by post-processing it, we get this approximation ratio for a solution that satisfies both GF and DS simultaneously. Similarly, for alpha DS, we get this approximation ratio for GF plus DS. This is the picture we end up with for the price of fairness. In general, it's unbounded once you impose an additional constraint, with the exception of imposing DS on a GF solution. And we basically find that both GF and DS are incompatible with a set of distance-based fairness notions. All right. So in conclusion, what did we do? We made some progress in understanding how different fairness notions relate to one another in fair clustering. One can possibly see other projects where you pick different fairness notions and see how you can satisfy them simultaneously. Or, by the way, the fact that some constraints are incompatible, that doesn't mean we cannot completely satisfy them simultaneously. We can, for example, introduce violations for the constraints and trade off the violations. So it's possible to pick other fairness notions and basically see how to satisfy them simultaneously or trade them off. But a good question is, does this approach actually make sense? Like when I say this approach, does this approach of having multiple fairness constraints and seeing how to basically satisfy them simultaneously? So we have at least seven different constraints in fair clustering. It doesn't seem that this is a scalable way of solving the problem to introduce more constraints and satisfy them simultaneously. This can get complicated. It can get complicated if we wanted theoretical guarantees. I think it's still complicated even if we were to use heuristics, right? So we think that other approaches might be more meaningful, such as, for example, an approach based on welfare and utility. That is basically, we pick a specific instance, we see how the clustering output affects the utilities of the individuals, and then we may define a welfare function and we try to optimize it instead of imposing a constraint on the clustering problem. Or possibly in some settings, we can have a good understanding of the application. And once we have a good understanding of the application, we can actually rigorously justify why this fairness notion is the specific one to satisfy. All right, that's all that I had. Yeah, thank you.
Well, thank you for the great talk. Yeah, so now is a good time for questions. We have about a bit more than 5 minutes. So if anyone has the question, please go ahead. If not, I have a question for you, but I want to hear from everyone else first.
Can you go back to the summary slide?
Right.
So I wonder if for the picture on the left, is it the case that usually DS is better than GF? I mean, is the cost of getting DS? So you have this picture where it's unbounded on both sides. From ordinary clustering to, but I mean, the asymmetry here in the picture kind of makes me wonder if in standard cases, DS would usually give a better solution in terms of the price of fairness for DS will be lower than the price of fairness for GF.
Right, that's a good question. Right, let me think. So both of them can be unbounded. All right. In the
One can be more unbounded than the other.
yeah, I get you. Okay, so if I have, I think the DS is less than or equal to GF. Yeah, but I don't have a proof actually. But I think this can be proved probably. I think that's probably that statement is probably correct, and it can be proved that DS is less expensive than GF. And this is actually a good question. So if you have different fairness notions, then you can also have an understanding of the price of fairness for them. So some of them are more expensive than others.
I guess that one corollary of what you've shown is that the price to move from DS to GF is unbounded as well.
Right. Yeah,
Yeah.
from DS to GF, that's basically unbounded.
Oh, to just GF, the price from DS to just GF, just as a corollary of what you said, it says of your proof is that just moving from DS to GF would be unbounded.
Right. So when I say moving, I mean in addition, you satisfy GF.
Yeah, but I'm saying even if not in addition, just instead, wouldn't, or perhaps I'm misunderstanding, because otherwise you can go to just GF and then go move from GF to GF plus DS. And then this would give you, because from GF to GF plus DS you have bounded.
Right. Okay. So yeah. So
I may be completely confused. Sorry if I'm.
no, yeah. So the arrow actually so represents. It's not like a direction in solving. It's like the optimal solution of the problem once you have the DS constraint. So you can sort of even ignore this arrow. What this is saying, the optimal solution of the problem for GF1 with the constraint GF plus DS. So if you take opt of GF plus DS divided by opt of DS, it's unbounded.
Right.
It doesn't matter how you solve them, right? It
Right.
doesn't matter how you solve them.
Right. So okay, probably I'll ask it one more time, but again, perhaps I'm misunderstanding, but then I'll leave it. Then isn't a corollary is that the opt of just GF over the opt of just DS is also unbounded.
Yes, we actually showed this, yes.
Yeah.
The,
Okay.
no. Yeah. What you're saying is a different statement. That the opt
Just by the picture, because otherwise, because the opt of GF over the opt of GF plus DS is bounded, and the opt of DS to the opt of, I mean, okay. Never mind. Okay, sorry. I my question is taking too long, and I don't want to give other people the opportunity to ask questions. Sorry.
I was wondering if in the like distance metrics that you said are like incompatible with GF
Right.
and DS, does this also include the sort of like stability-based notions of fair clustering?
Oh, the stability. Yeah. So the stability notion, we did not study it actually.
Okay.
Right. I think we were not able to show this, otherwise we would have had it actually included. So yeah, there was also another notion, the equitable notion. We were also unable to show that for it as well, I think. That is not incompatible. But yeah, my memory is not, yeah, it's been 7 months, so I don't remember exactly what the result was. Yeah.
All right, thank you.
If there is no other question right now, can I ask you just a super quick question? Can you actually go back like to the beginning of your talk towards the fairness definitions and everything? Where yeah, completely at the beginning on the slide where you were defining I think GF and yes and stuff. Because as you just mentioned, like at the end of your talk, right, there is like a lot of ways you could define fairness here. And like one thing that I was thinking when I was saying this, I don't know if it's interesting, actually, I'm asking you, but like one thing that I could think about, for example, is I'm looking at this example that has GF and yes, right? And say I look at group one, and I'm saying, okay, well, there's 4 people that are red in group one, but there are going to be in the end kind of like represented and summarized by someone that's in group blue. Could that be an issue? Could that be a fairness concern you have there? Could that be an interesting direction to look at?
Okay, so say that again. So you're saying that the red points here are represented.
Right. So basically, if I go back to our motivation, which is okay, since the center of the cluster is the point we're going to use to represent this cluster, and I'm using someone who's from the blue group to represent the cluster that has a lot of people from the red group. Do you think that would be an issue? Do you think there's something that could be interesting here?
Yeah. So yeah, that's definitely a good motivation, right? I'm just thinking. So there might be, for example, the center is supposed to be close to the points in the cluster, right?
Yeah.
So if we ignore, for example, group memberships, you wouldn't have this issue, right? Because the center is already close to the points in the cluster. So what you're saying is the groups, blue groups represented by a red center. So that is actually a good point. Yeah.
And this actually kind of relates to these like stability notions, right? So the idea there is that like no point would prefer to be in another cluster than the one it's in.
Mm-hmm.
And usually I think that's encoded by like a distance metric or something, but you could also think about it as like a like in terms of preferring to be close to people who are more like you or something like that.
Right.
Though it's interesting because then it definitely seems in direct tension with, you know, a lot of these notions of fairness.
Yeah, I feel like it's like a completely different notion of fairness. I was just like wondering if that would be an interesting thing to look at.
Yeah, I think it's interesting. Yeah, but I don't know why. I don't know if there's something that's already in the literature that basically translates to this, or you know, a simple thing that you can do to basically satisfy this notion you just brought up.
Yeah, it feels like, it would actually have the opposite problem in this case, which is when you have people from the red group and the blue group that are really close together, you want to cluster them together, but when you impose the definition of fairness, you actually don't want to do that anymore, for example. Yeah.
Right.
So, but I don't know how that would work out. I was just curious. Oh yeah, I mean, thank you. Yeah. Any other question or? All right, then I think that's it, and we can call it a day. So thank you again, Sayed, for the really good talk, and good to see everyone again. Um, we're going to keep this going for the semester, so we're going to have another talk next week, and I'll send information about this pretty soon. So hope to see you guys soon. Bye.